Now we will set up the case for turbulent flow. So if you go to general and check your case first, then you will see the minimum volume. Our minimum volume is a positive number, so our domain has no problem. Now we will solve this turbulent flow problem with pressure based solver. Our velocity formulation will be absolute and it will be steady state. Here in the modeling section, our energy equation will be on, so turn on the energy equation. In the viscous model, go to edit, and here you have different turbulent option. You have 1 equation, 2 equation, 3 equation, 4, 7 different types of turbulence model. You also have large eddy simulation, the ADS modeling. So right now we will do a very simple and most commonly used turbulent model, that is K epsilon model. So if you select K epsilon model, then you will get the options for K epsilon model. K epsilon model itself has 3 different models. One is standard K epsilon, another is RNG K epsilon, and other number 3 is realizable K epsilon model. So for simple CFD problem, we will use standard K epsilon model. If you know the problem setup, the problem definition, and the types of your problem, then you can use RNG and realizable. But if you don't know what specific type of problem you are trying to solve, always stick with standard K epsilon model. You can find lots of literature based on turbulent model, especially K epsilon model, and for standard RNG and realizable problem, you can study different flow phenomena and when we have to use realizable, when we have to use RNG. You can learn all of those things from literature or from CFD online. But for now, we are interested on how to set up the case for turbulent flow. So we are taking standard K epsilon model as our viscous model, and here you have another option for the wall treatment. So turbulent model always assume the wall with different approach. Standard K epsilon model has different types of near wall treatment. Here we have 4 different types of near wall treatment. Number 1 is standard wall function. Number 2 is non-equilibrium wall function, enhanced wall treatment, and user-defined wall function. So this wall function is actually how the viscosity will change with your solid boundary to your fluid, and how the model will interact with the wall that dictates this near wall treatment. So for simple CFD, it's better to use standard wall function or enhanced wall treatment. So right now we will stick with standard wall function. Here in the model constant, you have different model constants. This is actually based on the K epsilon transport equation. So these constants are fixed. If you want to change this constant, make sure that you are taking the right constant. If you don't know, then do not change this constant for any types of turbulent model. For example, if you select K omega, you can see the constant has changed. So for different model, these constants varies. So do not change this constant unless you know what you are doing. So keep it as it is. And you can also define the turbulent viscosity if you know the types of turbulent viscosity and how it behaves with your flow field and your geometry. Then you can define your own turbulent viscosity function, otherwise leave it as it is. So select the standard wall function and select standard K-epsilon model, then OK. Now we have selected the turbulence model. We don't have any radiation, we don't have any combustion, any heat transfer or heat exchanger, so we will leave it as it is and we will go to material. Here our material, our working fluid is air, so air is selected. You can check the property of air here. If you think these properties are okay, then you can close it. Then go to cell zone condition. We have a single domain, so that's why we have a single zone, and the type of this zone is fluid. If you go to edit, you will see the parameters. The material is air. We don't have any frame motion or mesh motion or porous zone, so nothing is selected. Then you select the OK. Now the boundary condition. This is the most important part for turbulence modeling. If you go to inlet, the type of your inlet is right now velocity inlet. You can change it to pressure inlet or mass flow inlet, but right now we will stick with velocity inlet. So if you select the velocity inlet, then you will get this window, the velocity inlet window. Here you have the velocity specification method, that is the magnitude and normal to boundary. That means we will give the magnitude of the velocity and it will act normal to the inlet boundary. You can give a component if you want. So if your velocity is not normal to your inlet boundary, you can change the x, y, z velocity component, then it will go at an angle with the inlet. If you think that your velocity is the normal to the boundary, then you can stick with magnitude and normal to the boundary. Now reference frame, our velocity is absolute, we don't have any frame motion. And the velocity magnitude, what is the magnitude of our velocity? Right now it's 0.028. that is the previous velocity when we tried to model the laminar flow problem, and the velocity was 0.028. but for turbulent flow, definitely our velocity will be much higher, and we will find it based on our Reynolds number. So here is the calculation for velocity. As you can see, the Reynolds number right now 10,000, and the dynamic viscosity is this based on the material property, also the density based on the material property, and our characteristic length is the diameter, that is 2 inch. So if you put all of this value here, you will get the velocity 2.874 meter per second. So this is the velocity we need for Reynolds number 10,000. So put it 2.874. Okay, and the operating gauge pressure is right now 0. So the fluid is flowing from atmosphere and it goes over the cylinder and it goes through the outlet. So our gauge pressure is 0. The thing here, the new thing is here, the turbulence option. You don't have this option when we try to model the laminar flow. For an instant, if you go here to model, go to viscosity and change it to K epsilon to laminar, and OK. And if you go back to inlet boundary condition, then you will see you don't have any turbulent option. So go back to model, viscosity, K epsilon, standard wall function, OK. Go to boundary condition, go to inlet. Now you have the turbulence option. So this turbulent option means we are doing the K epsilon model, the K is the turbulent kinetic energy and epsilon is the turbulent dissipation rate. So we have to specify these two values. Either you can specify the K and epsilon value, you can specify the intensity and length scale, you can specify intensity and viscosity ratio, or you can specify intensity and hydraulic diameter. You have to provide one of these two values. So in general, we use the intensity and hydraulic diameter. Turbulent intensity itself is a very complicated mathematical term. We have to find it by statistical analysis. If you want to learn about turbulent intensity, you can go to CFD online and you can check this description, or you can go to any turbulence book and you can check the definition of turbulent intensity. It's a ratio of velocity fluctuation over mean velocity. So here you have the option for turbulent intensity in percentage. Right now the default value is 10. That means your fluctuation is 10% higher or lower than the mean velocity. So you can change this. If you have a very high turbulent flow, you can change the intensity. If you have a low turbulent flow, you can also reduce that intensity. But right now we are assuming that the turbulent intensity is 10%. You can calculate the turbulent intensity based on this formula here. So right now the turbulent intensity is 10% and the hydraulic diameter. The hydraulic diameter is really easy to calculate for internal flow. We have lots of formula for calculating hydraulic diameter. And for external flow, right now we are considering the hydraulic diameter is the diameter of our cylinder, that is 2 inch. That means 0.0508 meter. Always check this. Well, here it's in inch, so we can only use the inch option. So 2 inch, select OK. Before doing that, you have the thermal option, so change that. We don't have any radiation, no combustion, no multi-phase flow, only the momentum and thermal. So here is the inlet boundary condition, select OK. Now the outlet is outflow, just like the laminar flow, so we don't need to change anything. So the velocity is 2.874 and the thermal is 298 because this is the inlet air temperature. The cylinder wall has the temperature of 353. So this is the wall boundary condition. Select OK. You don't have any turbulence effect on that wall. We just need to change the inlet turbulence boundary condition from laminar to turbulent. And symmetry, we don't have any change in symmetric wall, and that's it. We don't have any dynamic mesh, so we don't need to worry about this. Reference value, these are the reference value. As you can see, if you go here compute from inlet, then you can see the change, the temperature, density and velocity. Now go to solution method. We will use the simple scheme for pressure velocity coupling. For spatial discretization for gradient, we will use least square cell based, just like the laminar flow. For momentum, it will be second order upwind. For turbulent kinetic energy, it will be also second order upwind, and turbulent dissipation rate, change it to second order upwind. Solution control, these are the relaxation factors here. As you can see, for turbulent model we have some extra relaxation factors. One is turbulent kinetic energy, another is turbulent dissipation rate, turbulent viscosity and energy. So right now turbulent viscosity and energy has no change. We are dealing with the K and epsilon value. and pressure and momentum value. In monitor option, we have the convergence criteria and the print and plot option. We select all of this. We will see the continuity, the x velocity, y velocity and z velocity, and also the k and epsilon value. Solution initialization, we will initialize the solution by hybrid initialization. So select initialize and it will initialize by 10 iteration. Then go to calculation and run it 100 times. So start calculation. Now your solver will start calculating all of this. As you can see, it is taking more time than laminar flow, which makes sense because turbulent flow has some extra equation, so it takes time to solve that equations. And here you will see the curves. The white one is for continuity, the red, blue and green one is for x, y and z velocity. You have also the energy equation and the turbulent kinetic energy, which is the pink line, and you have the epsilon, that is the yellow line, it's the turbulent dissipation rate. So you can see this right now. For turbulence, you have a slight change with the turbulence. So our solution has been done. As you can see, we have velocity and continuity is a very convergent behavior, but we have a fluctuating behavior for the k and epsilon value, that's the turbulent parameter. So in the next tutorial we will see the results and we will compare with the laminar flow problem.